Okay, let's jump right into this explainer. We're looking at a completely incredible breakthrough out of MIT, just published in the journal Nature Communications, and it's poised to totally change how we capture the world around us. They've basically taken bulky, complicated infrared cameras and figured out how to shrink them down onto a tiny solid-state chip. It's an absolutely fascinating leap in engineering.
So it raises a really fascinating question. What if a camera lens had literally zero moving parts? To get why this is such a massive deal, we have to think about how cameras have historically worked. For well over a century, if you wanted to change focus or adjust what a camera was capturing, you had to physically move pieces of glass or mechanical parts. And even today's super advanced infrared systems still rely on those fragile physical movements. But what if we could eliminate all of that physical bulk? What if the lens itself was totally stationary, yet infinitely adjustable?
Section 1. The bulky camera problem. To really grasp the magnitude of this breakthrough, we first need to look at the physical limitations we're currently stuck with.
Look, conventional infrared systems are undeniably useful, but man, they are incredibly bulky. Because they rely entirely on mechanical components to change focus, there is a hard physical limit on how small, durable, and efficient they can actually be. But contrast that old mechanical reality with this new MIT design, it is completely compact. It's built directly onto a semiconductor chip, and rather than shifting fragile parts around, the light is controlled entirely electronically. It takes something traditionally mechanical and transforms it into something microscopic and digital.
Moving on to Section 2, MIT's pixel-level breakthrough. Let's see exactly how they achieved this technological leap. The secret sauce here is dynamic pixel-level control. The researchers basically built a programmable infrared lens right onto a semiconductor chip. There are absolutely no moving parts involved. Instead, each individual microscopic pixel on this chip can adjust its optical properties completely independently. Think about the sheer power of that for a second. The lens can dynamically adjust how it interacts with incoming light at the level of a single pixel. It allows the camera to collect totally different types of information from the exact same scene all at once.
And to prove this concept actually works outside of theory, the team successfully fabricated and tested a 6x6 metasurface pixel array. Now, okay, 6x6 might sound tiny, but as a laboratory-scale prototype, it is monumental. They proved that this microscopic array can repeatedly switch states without losing any functionality. And honestly, the most exciting part? They built it using manufacturing processes that are already super common in semiconductor chip fabrication. That means this technology is basically ready to be scaled up to massive industrial levels.
All right, Section 3. How the chip works. Let's look under the hood to see the physics in action.
The core of this entire innovation is a programmable metasurface. Simply put, this is a surface that dynamically controls how incoming light is manipulated. Now, metasurfaces themselves aren't brand new, but previous versions had a pretty fatal flaw. They either had to control the entire lens all at once as a single unit, or if you wanted pixel-by-pixel control, they required impossibly complex wiring that caused severe electrical interference. Scaling it up was basically an engineering nightmare.
But the MIT team totally solved this. They combined a specific material with a highly clever network of wires. Here is the exact three-step sequence happening on that chip. Step 1. At the precise intersection of these copper wires, a highly localized burst of heat is generated through doped silicon. Step 2. This heat hits a phase change material, causing tiny regions of that material to instantly switch physical states, literally flipping back and forth between a crystalline structure and an amorphous structure. And finally, Step 3. This rapid change in state directly alters how that specific pixel interacts with incoming mid-infrared light. So they're essentially using tiny bursts of heat to bend light on command.
So how did they manage all those wires without that crippling electrical interference we talked about? Well, as Jojin Hu, MIT's professor of materials science, explains, the breakthrough is actually borrowing from everyday technology. He notes that the key innovation is their crossbar architecture. He says, "We didn't invent this architecture, it's used in displays, but it's the first time anyone's used it for active phase change metasurfaces." The absolute brilliance here is using a crossbar network of copper wires, just like the ones inside the screen you might be looking at right now, to completely solve the issue of unintended currents. And calculations show this architecture will safely scale up to potentially millions of pixels.
Section 4. Smarter imaging applications. Why does this pixel-level control actually matter to you and the real world?
The applications for capturing mid-infrared light are huge. Why mid-infrared specifically? Because a lot of gases and organic molecules readily absorb light in this exact wavelength. This means this technology gives us the power to instantly detect dangerous chemical leaks like methane and propane. As the study's first author, Cosmin Constantin Popescu, points out, it provides vital tools for atmospheric environmental monitoring, allowing us to track specific compounds in the air to protect our communities. Plus, it can give us much deeper insights when studying space. It can completely shrink down thermal imaging, and it could radically upgrade military hardware, taking bulky night vision goggles and making them incredibly compact and smart.
Which brings us to Section 5, the future of optical computing. This is where the technology gets truly sci-fi, moving far beyond just taking better pictures.
The research team believes these programmable metasurfaces are a massive stepping stone to optical computing. Think of it as thinking with light, performing complex computations using light particles instead of pushing electricity through conventional electronic circuits. Just imagine a future version of this chip where the camera doesn't just passively record a scene. Instead, it actively computes the incoming light to instantly highlight specific objects or patterns based strictly on what the user wants to detect. We're talking lightning-fast data processing happening at the optical level before it ever even becomes a digital image.
As the team at MIT continues to increase the pixel count and durability of these chips, we are staring down a fundamental shift in both imaging and data processing. It really just goes to show how much untapped potential still exists in the realm of semiconductor manufacturing. And it leaves us with one truly profound question to consider. What happens to our world when light, not electricity, powers the future of computing?